So I'm Lauren Bennett, and this is my colleague Flora Vale. We are going to be talking about spatial statistics, what the simple ways to do more with your data. I'm on the spatial statistics team in Redlands, so that's the development team. We work on building all the tools that we're going to be talking about today. Flora is an honorary member of that team since she started at Esri, has been working with our tools, and she created the slides today, which I think you will all agree are like the most awesome slides ever. So just keep that in mind. She's the best. And we're going to be, we have to decide what workshops we're going to do. We have to name them and give them little paragraphs in like February. And so February is really far away from July. We're like, oh, we're going to do this, and we're going to do this, and it's going to be so great. So in February, we had this brilliant idea that we were going to do a workshop where we were going to explain every single tool in the toolbox. And we were going to demo every single tool in the toolbox. And it was going to be great. It is going to be great, but it was we had moments of just like, why? So this is the first time we're doing this session. We're really excited about it. It gave us an opportunity to dig into some of the tools that maybe we don't use as much as others, because just like we have our favorites, but just like children, we really love them all equally. So we're going to have a little fun today, I think. So I want to, sorry.
Is there going to simulcast in 11A?
Okay. Okay, so they are going to simulcast this in 11A, which I guess means the slides and the words will be, will there?
The slides and the audio.
Okay, the slides and audio will be broadcast from 11A. You missed this, but you'll get, I know, that's not, they're all going to run right now. I don't want to see that. So 11A, if anyone, when you get tired of standing, you can make your way to 11A. We will not take it. And now even those of you who in the middle are like, I don't want to look at this, we'll just assume you're going to 11A. There should always simulcast. That's so great. Okay, so I want to start by talking about what are spatial statistics, since we are going to spend the whole session talking about them. If you looked it up in the dictionary, you would find kind of boring definition that would say that spatial statistics are a set of tools, methods, techniques that allow you to explore spatial patterns, spatial distributions, spatial relationships that exist in your data. And that is true. That is what they are. I do think it's really important to note that these are not just traditional statistics that happen to be applied to spatial data. These are tools that inherently take into account the spatial nature of your data. So that includes things like proximity, area, length, orientation, how things are connected, coincidence and distance, direction. There's all these different ways that we use the spatial characteristics of your data in the mathematics of these tools. So they are truly spatial statistics. And I just think that's a really important thing to know. A lot of the time, that idea of connectivity or relationships, a lot of times it's this proximity that we're using to determine in terms of how we use it in the math. But you'll see we use all sorts of different aspects of your data throughout the tools as part of the underlying algorithms and methods. Now, all of that aside, the truth is that spatial statistics are really just this extension of what we do naturally every time we look at a map. It's what our eyes and our minds just do when we look at a map. When you look at a map, a thematic map, a point map, whatever it might be, you're instantly, oh, there's a cluster over here. What's going on? I see that there's not a lot happening here. Why is that? So first we see these spatial patterns, but our brains are also incredibly good at starting to understand relationships. So if you're looking at a map of an area that you're familiar with and you see a pattern, you go beyond just saying, oh, there's a cluster over here. Then you're saying, well, I know something about that area. It must be related to these things, or these variables must be important. So we instantly, every time we look at a map, start doing that. That's why maps are so powerful. But I think this really comes down to what makes spatial statistics so important. It's why It wakes me up in the morning. It wakes Flora up in the morning. It's this question. I think we see it. I think it's becoming something that's being talked about. This idea is something like a spreadsheet. Is that data or information? This distinction is being made between data and information. Just because you have data doesn't mean you know anything, right? Data itself isn't enough. We have to turn that data into information. And I would kind of argue that the same is true for maps. I mean, is a map data or information? Of course, I don't think a map is the equivalent of a spreadsheet. I think a map we're getting there. We're starting to turn that data into information. But I kind of think of it like we have 1 foot in data and 1 foot in information when we have a map. We're still just looking. If you're thinking about a thematic map, all you've done is put the numbers in your spreadsheet on a map. You're still just looking at numbers, essentially. Now they're color-coded. But we can do more than just look at thematic maps, or just put points on a map. So whenever we look at a spreadsheet, I don't know about you, but I cannot just look at thousands of numbers and make sense of them. So when I look at a spreadsheet, I immediately want to do things like, what's the average value? What's the standard deviation? What's the minimum value? What's the maximum value? Very simple descriptive statistics, but it's the only way that I can boil something like a spreadsheet, all this data, down into information. Very simple information, but it's the only way I can really start to make sense of that data. And the same thing goes for maps. We can do more. There are ways that we can go beyond just that visualization, the equivalent of looking at a spreadsheet, and turn that data into information. And spatial statistics are a really powerful way to do that. So with that, I'm going to pass it over to Flora. She is going to be going through the slides, and I'm going to be given just a couple of demos.
I think you keep that mic.
Oh, okay.
Hello. Is this loud enough? Should we turn
Do
it
you
up?
want to just switch on and off? It doesn't sound. Is it loud enough?
Is it all right? Okay. Let's do this. All right. So we are really going to go through every single tool in the toolbox. There are 21 tools that we're going to go through. So I think we have probably less than an hour left at this point. So it's going to be fast. And the goal here is not to turn you into experts for all of these tools. The goal here really is to make you aware that the tools exist, maybe to get you excited to want to learn more, and maybe inspire you to look at your data in some new ways. And if we do inspire you to want to learn more, we have lots of other workshops. And at the end of the session, I'll put the schedule up so that you can see when you can come and get more specific information about the different tools. So also, before we start, I just wanted to point out that these little script symbols next to the tools mean that they are Python scripts. So you can actually look inside and see what's happening. There's no secret. The math is right there. It's not a black box tool. You can see exactly what's happening, and if you are so inclined, you can even tinker around with the code and maybe make some adjustments. I do recommend, though, that you make a copy of the original script before you go changing things in there. But, that's my warning.
That's learned from experience.
Yes. Okay, so the tools are broken down into different tool sets. So we're going to go tool set by tool set. And we're going to start with measuring geographic distributions. So this tool set is kind of like the descriptive statistics that you would use with, just non-spatial data. So we're going to look at things like central tendency and distribution, standard deviations, that sort of thing, to kind of measure what's happening with our data. So the first tool we're going to look at is central feature. So central feature is going to identify the feature that is at most center. So let's see what that looks like. Let's say we have a set of points. We can measure the distance from each point to all of the other points. And then we're going to see which of these points has the shortest distance to all the other points. And that feature with the shortest distance will be the central feature. And the tool actually output a feature right there. And so Lauren's going to show you how that works.
Okay, so this is an example of a good use case for using the central feature tool. So what we have here are all of the locations of fire stations. And what we want to do is the battalion chief wants to move his office so that he's in the fire station that is most centrally located, so that he's close to all of the people that work for him. So he wants to choose the central location. Very simple analysis, but would be pretty difficult to do just looking at a bunch of points on a map. Sure, you could get into the general area, but which one really is the best one? We might as well pick the truly best one. So we pick those stations, and we can run the analysis. Now we have options. He might want to weight those stations that have more employees more. So we can weight these descriptive statistics so that those locations that have more importance in our analysis can pull that central feature. So we can do that here using the number of employees in each of those locations. And when we run that analysis, it returns to us the location of that central feature, and we can re-symbolize that quickly so that we can see it. And we can see that it lines up here with station number 5. So really simple analysis. And I think what's important, and I think it is that these tools are incredibly simple, but they can also be really powerful to solve problems. So that's central feature.
All right, next on the list is mean center. So mean center is going to identify the geographic center of your features. And so with central feature, you're actually choosing one of the features that is the most central. With mean center, you're putting a new feature where the center of all of your features are. So that's going to look like this. We're going to actually take the average of all of the lat longs, and then that will become our mean center. So let's see what that looks like.
All right, so now you're thinking, please don't demo mean center. That's ridiculous. But actually, mean center can be really powerful. It's not always, and I think this is true for a lot of the tools that we're talking about, particularly in measuring geographic distributions, but really in a lot of the spatial statistics tools in general, some of the most powerful ways to use these tools is to look at things either over time or to compare different distributions. So in this case, what we're going to do is we're going to look at the mean center of population in California. And so we're going to use our population data for 2010. We're going to weight it by population, and we're going to run that analysis. And so we can see where the mean center is currently for population in California. And it's no surprise that it falls somewhere in between Los Angeles and San Francisco, because those are the two big population centers in California. But what about 100 years ago? Would the mean center have been the same in 1900 or 1950? What would that look like? And so what we can do is actually use mean center, run it multiple times for each of these different time periods, and what we end up with is a bunch of mean centers, and we can see them. We can see the one for 2010, 2009, 1990, and all the way back to the year 1900, and we can see how that changes. And one of the really powerful ways to look at this data is actually to animate it. And so if we go in and create a group animation with the mean centers group layer here, and I think I can't remember if I have to invert the order, so we'll see. We'll see soon enough. Where does it start? Yeah, so we can see it's just turning layers on and off in that group layer. So I have a group layer, and it goes through, it turns on 1900, 1910, 1920, 1930, and this is reflecting this shift in population, which started when people moved to California in the gold rush. Then Los Angeles became kind of the place to be. Hollywood became kind of known throughout the world. People started to move down to Southern California until now what we see with this kind of distribution right in the middle there. So a ridiculously simple tool that, as Flora showed, you could basically do the math by hand for, but you can still really get some meaningful information if you use it in kind of the right context.
All right, next, median center. So median center is similar, but it's more robust to outliers. So again, it's pretty simple. We're actually going to take those lat longs and then find the median value for each, and then that will become our median center. So I think we'll switch over, and then I'll explain the difference.
Okay. So a really good use case for median center here, we're going to cite a library, not just for reading, but also for access to the internet in this community where there are a lot of the population doesn't have access to a computer at home. We want to give kids access to computers and the internet in the library. So we're citing libraries, and we don't just want to cite one. We actually want to cite one in each district. So one thing that is really awesome about a lot of these tools is another parameter that I haven't used yet. So if we look at the patron locations, and in this case, we don't want to weight it. We actually want to use the case field. And so essentially, this case field, what it will do is we give it a field in our data set. And for each unique value in that data set, it's going to group things together and create its own median center. So it's not just going to create one median center, it's going to create three. This field right here, district, each one of those patrons has a 1, 2, or 3 associated with it. So it'll find all the 1s, create a median center, all the 2s, create a median center, and all the 3s and create a median center. And so we can see the output of that if we turn on, we change the symbology here, we can see those 3 locations in each district that are created based on that case field. So another really useful thing, in this case we're trying to create 3 median centers for these locations, but we could also, again, use this for comparison. If you had, if we wanted, let's say each of those districts were different gangs, and we wanted to see the mean center of graffiti incidents for each one of those gangs, we could compare where their median centers are using that same case field. So another kind of powerful thing about those tools that a lot of people don't know about.
All right, and you might be thinking, those seem pretty similar. What's the difference between the mean center and the median center? So to illustrate that, I'm going to add an outlier up in the top corner there, and then we'll see what happens. So the mean changes and the median changes based on the outlier. So this is where they were to begin with before the outlier. With the outlier, the mean moves all the way up there. The median only moves this far. So it really depends on what your question is, but the median is definitely less affected by outliers, and the mean is really just the true mean. So next up is linear directional mean. So this is going to be for linear features, for lines. And it's going to identify the average direction that our lines are pointing. So to illustrate that, we'll take a look at a set of lines, and then we'll measure the angle each line has, and then the average of those angles will become our linear directional mean.
So one pretty cool example of how we could use this, this map, which is clearly very useful, is looking at, it looks like one of those things that you used to have when you'd put the pen in it and just circle it around. Spirograph, those things were awesome. This is not awesome, though. This is a really big mess of data. And so it's hurricane tracks. It's hurricane tracks for many, many, many years. And what we want to do is understand, have the average directions of those hurricanes changed over time. And so what we can do is we can run the linear directional mean tool. This time we're going to run it on those hurricane trajectories, and we're going to use a case field again, which is going to be the year. So we don't want the average for all years. We want yearly what was the average. And so it's going to create one for each of those. And I think it is pretty amazing how quickly you get the answer to this, because that is a lot of hurricane data. I think this goes back to somewhere in the 1890s. And 38,000 hurricanes. And we get this result, which of course isn't quite enough for us to understand, because all we see is each year. We don't know which is which. So what I'm going to do is I'm going to make a version of this that is symbolized by year. So I'm going to use the year data set, add all the values, they're in order, and I'm going to bump up the symbol just a little, and that'll be on top of our arrows. And so now we can start to see the darker arrows are the more recent, and you can see that this data goes from 1850 all of the way until 2008. Wait, let me do that again. It's not doing it. There we go. So now what we see is the lighter ones are more the ones in 1850s all the way up to the darkest ones in 2008. And we can start to see if there's any sort of change in direction. I'm not sure I've come to a conclusion on this one, but it certainly is a lot. We're getting a lot closer to turning those tracks into information than we are just looking at all the tracks at one time.
All right, now we'll move on to standard distance. So standard distance is, it measures the degree of concentration or dispersion of your feature. So think of it kind of like the standard deviation of a set of numbers. You want to know what the variance is. Here we're going to see what the variance is in our locations. So we'll take a look at what that looks like. We start with our mean center, and then we're going to take the standard distance to all the other features, and that will become the radius for our standard distance. And you can have 1, 2, or 3 standard deviations of the standard distance. So we'll see what that looks like.
Okay, this is actually pretty cool, and we're looking at 2 bookstores in the San Francisco area, and we have the locations of the customers for each, the people that belong to their loyalty clubs for each of these bookstores. And so what we want to do is see which one has a larger distribution throughout the city, kind of a bigger pull, essentially. So we're going to run the standard distance tool. Again, you'll see we're going to use that case field, comes in quite a bit. We're going to use the store, and we'll run it, and it's going to create 2 of these standard distance polygons. And we immediately see that the Steiner bookstore has a pretty significantly smaller distribution than the Bosworth bookstore, and we get a picture for those. And it's, interestingly, they don't overlap at all. That overlap would be a pretty interesting place. And if you're in another bookstore, the gaps are an interesting thing to know about too, because that is a place where there's a gap in service. So that is standard distance.
All right, directional distribution or standard deviational ellipse. So this one is pretty cool. So it's also looking at that standard deviation, but this one actually takes into account the directional trend of the data. So again, we start with the mean center, but then we actually find the standard deviation of the x-axis and of the y-axis to make a tilt for our ellipse, and that becomes our standard deviational ellipse. So let's see how that we can use that.
So this is actually one of my favorite tools, which I know sounds kind of crazy, but I think it's just really powerful. Whenever I have a point data set, especially if there's any sort of temporal aspect to it, I almost immediately run this tool just to see any sort of trends that might be there in the data. I mean, alternatively, so this is Ushahidi data in Libya. This is data that Ushahidi is a crowdsourcing application that essentially is especially stood up during times of crisis. And so these are essentially requests via SMS for humanitarian assistance. And one thing we could do to look at this data is just have it turn on and off over time, because that would be super useful. But I think we can do a lot more than that. So the ellipses help us do that. And so we can run the ellipse tool. And in this case, we're going to use the case field, but it's a little bit different. It's not a type. It's actually time that we're using. And what I've done, if we look in the data here, is I've basically grouped together all of the first week worth of data, second week worth of data, third week worth of data, and each one of them has a unique number. And so when we run the analysis, it's going to create a number of ellipses, and we can take a look at the in a similar way. I'll bring in all that yearly data, and the darker green ones are the ones that happened in the beginning time periods, and the most recent is in red. And so we pretty quickly get a clear picture that the trend has been pretty dramatically changing over time. And And what I think is really powerful about a lot of these tools is that they can be a really critical part of the data exploration process. You get a new set of data, you just want to understand some of the things about that so you can guide your questions, actually. Because in the beginning, our question is what's going on? And now our question is why has the pattern shifted? What has caused this shrinking in the distribution and also the movement of the distribution? And so rather than just what's going on, we have very kind of clear questions that have been driven by some of this introductory, descriptive, exploratory analysis.
And that concludes the Measuring Geographic Distributions toolset. So 1 down, 3 to go. Next up is analyzing patterns. And I would like to say I think they get more exciting as we go through, but maybe that's just
That's
me.
not true.
So, analyzing patterns toolset. So this, we have lots of different ways to measure if our data is clustered, if it's dispersed, kind of get the degree of which our data has patterns. So the first tool is average nearest neighbor. So we're actually going to create an index to see if our data exhibits clustering or not by looking at the nearest features to each feature. So we're going to actually measure the distance between each feature and its nearest feature. And then we're going to get the average of all of those distances. And then we'll compare that to an expected average distance based on a random distribution. So then we'll create a ratio, an average nearest neighbor ratio. So we'll take the observed and divide that by the expected. If that ratio is less than 1, then our data is clustered. And if the ratio is greater than 1, then our data is dispersed. So do we have a demo for that one?
Yes.
Yeah.
Yeah, we have demos for all of these, and actually, up until now, every demo that I've given was created by Janora, who's standing back there.
I was going to ask her to raise her hand at the end.
Yeah, raise your
Nice
hand.
to meet you. Thank you for your help.
She's the best, and she really helped us out a lot. And I think learned a little bit about the spatial stats tools along the way, so it wasn't a total loss there. So this example is looking at tornadoes in the Great Plains region, and so we want to look. So of course we know that tornadoes cluster, right? We know that they are obviously much more likely in this region than they would be in Connecticut or California. But what about within this region? Would we expect there to be clustering in this region, and is there clustering, and can we explore that? So we're going to use the average nearest neighbor tool to explore that. So I'm changing toolboxes here, going to the average nearest neighbor tool, using all of those tornadoes, going to get it to generate a report. Now these reports are pretty cool because it means, so we output a lot of information in our in this messages window, actually. So a little food for thought while this runs. How many of you leave background geoprocessing on and never have to look at this messages window? Oh, nobody. I love the messages window. But also the spatial statistics tools often rely on the messages window. We put a lot of output in the messages window, and you'll see in some of our tools it is the only output. This is a great example of one. So the output is a z-score and a p-value. Now the good news is you actually make it really easy. You don't even have to know what the z-score and p-value mean. If we look at our results, okay, how many people use the results window? Okay, not everyone raised their hand, so I'm about to blow some people's minds here, okay? Seriously, I don't even know how I would live my life without the results window. So if you go to geoprocessing and you go to the results window, there is this results option under geoprocessing. It stores every time you run a geoprocessing tool, which allows you to rerun geoprocessing tools. You can also you can drag and drop these into Model Builder, and if there's inputs and outputs, all of that comes along. Saves a lot of time there. The results window saves so much time. And one really great thing about the results window is it's stored with your map document. So you come back to a project 6 months later, and I'm sure this never happens to you, but it happens to me all the time. I have no idea what I did 6 months ago. I'm not sure what I did yesterday. So that list is still there. I can follow my whole workflow. And oftentimes what I'll do is I'll delete the ones that aren't relevant when I'm done. So I save really just the ones that I want to remember. And I use that as this really great way to save workflow. So I know that's a step off from what I was supposed to talk about. But I think it's really important.
It's an important step.
Yeah.
And it goes with map packages as well. So we can send each other a map package and see the analysis that was run in that map package.
Yeah, it's really good for that kind of collaboration too. So one of the other things you can do from here is if we do create a report or if we create a PDF, which some of our other tools do, you can click on that right from the results window. And this report shows us that given the z-score of negative 114, it's a very big z-score, that is very big, there is a less than 1% chance that this clustered pattern could be the result of random chance. So that's telling us that we have statistically significant clustering in those tornado touchdowns in the Great Plains area. So we get a lot of information there, and you don't even have to. We give you the sentence, we give you a picture, we give you the numbers. Got this for all kinds of learners and thinkers here. So that is the average nearest neighbor, and a little side step into results window and messages. Oh, and for those of you who don't know, if you go to geoprocessing options, there's two things. One, you can decide how long you want to keep your geoprocessing results. So I just always go in and say never delete. And the other thing you can do is this is where you can enable or disable the background geoprocessing. So if you do have it on and you didn't know how to turn it off, it's in this geoprocessing options. You can turn it off, and then that messages window will be there.
Okay, next up, spatial autocorrelation. So this is another way of measuring if your data is clustered or dispersed. But with this method, we're looking at the correlation between distances of features and the difference of their values. So do we have two features with high values that are near each other, or two features with low values that are near each other? Those low values and high values will have a short distance in data space between them. So if there's a positive correlation, meaning that as the distance from the features gets farther away, the distance in value gets farther away, then that means we have clustering. And if it's the inverse, if as the features get farther away, their values get more similar, then we have a dispersed pattern. So this helps us measure that.
Okay. So for this one, we're actually going to go back to California population because I think it's a good example of how we can use spatial autocorrelation also. Because we really use spatial autocorrelation in two ways. And so this idea of is it random or is it dispersed, it's very, or is it clustered, it's kind of a, you might call it kind of a stupid question in some ways, because we know things are going to be dispersed. It's very rare that things are random, right? We know people cluster together, crimes cluster together, income clusters together, disease clusters together. A lot of these things cluster together. And so it really, while it is useful to know, for instance, for the tornadoes to guide our decision making and to guide our questions, is there clustering? Oftentimes, these are most useful from a comparison standpoint. So in this case, we're going to use the spatial autocorrelation tool to see if clustering has been increasing or decreasing over time. We also use the spatial autocorrelation tool a lot when we do regression analysis, and we have a whole session on regression analysis, so if you're interested in that, we'll point you to it. But in regression analysis, one of the requirements of regression analysis is that our output is not clustered. We can't have clustered over and under predictions. And so we use the spatial autocorrelation tool to test to see if we have clustering, because it is a requirement of the tool. So those are probably the two ways I use it most, either to compare things over time or different distributions, or regression analysis. So in this case, I'm going to run the spatial autocorrelation tool on the data from 1900. I'm going to use my population data set. I'm going to generate a report, and I'm going to go. And so we can see right away it tells us what the z-score and p-value is. So I can tell just by looking at this, a very small p-value means we have clustering. And we can also take a look at that report. And we can see what that we can see that there's clustering, and we get the pictures, we get the words. Now, what I've done is I've actually run this analysis. I've run that analysis 10, 11 times for each one of those decades. And what I did after I did that is I created a little table that has what year it was and what the z-score was. And it's this table of information that I'm going to use to look at the pattern in clustering over time. And so we can go in and create a graph. And I'm going to create a line graph using year and z-score. And it's actually a really interesting one because we see that over time there was this decrease happening in the intensity of clustering. And then between 1930, around 1940, it starts to really pick up again, and the intensity of clustering starts increasing. So things were dispersing up until the 30s, and then starting in the 40s, they start to come together again and cluster again, which it makes a lot of sense if we think about, we know now everybody's coming, there's this movement into cities, right? So it makes sense that we're seeing this kind of clustering happening. So imagine looking at this as a thematic map, just changing colors, right? It would be really hard to figure out if there was a change in that kind of intensity of clustering, but with the graph, it's really, really easy to do. So that is spatial autocorrelation.
Do you ever use it to figure out a neighborhood size of autocorrelation?
Yes. Well, you're one step ahead of us.
So incremental spatial autocorrelation is next. And this tool is really, it's just a series of spatial autocorrelations run and put into a graph for you. So Lauren just now created a separate z-score for each of the years. But what incremental spatial autocorrelation does is creates a graph for you of the z-scores over different distances. So it's actually helping you decide the scale of your analysis. So for some of the other tools, we have to choose what we call a neighborhood size. We have to conceptualize spatial relationships. And so this tool helps us do that. It's actually going to run that tool a bunch of times for us and then output a graph. And that graph will identify the peak distance or the distance that exhibits the most clustering. And that number can be really valuable in some of our other tools, and we'll kind of touch back on that in a little bit. And so we don't really need to demo that one because it's the same tool. It's just kind of a model process of that tool happening over and over and then giving us a nice graph.
It's something I used to do a lot for analysis, and so I have the benefit of working on the spatial statistics team and sitting next to the developer, and I said, you know, I'm doing this a whole lot, and so our users are doing this a lot too, and I really don't want to run this 10 times every time I need to figure out a good distance band, so could you build a tool that does this for me and outputs a pretty graphic? And so he did, and that was really nice of him because it makes a big difference, and now all of you get to take advantage of it too.
All right, next up is high-low clustering. So again, this is another global measure to see if the data exhibits clustering. But the difference here is that we're not looking at whether the data is clustered or dispersed. We're looking at whether we find clusters of high values or clusters of low values. So in the math, before I said it was a correlation of the distance between the features in space and the distance in value, but now we actually take the product of the two values. And so if you get a really large number, that means that the data exhibits high value clusters, and if you get a really small number, you're exhibiting low value clusters. And so this is going to be more useful, again, for comparisons. All of these global stats tools are more useful when you're comparing one year to another or one place to another to see which one has the most intense degree of clustering. And so this one is just a way of measuring the intensity of low clusters versus the intensity of high clusters. The next tool that we have in the tool set is multi-distance spatial cluster analysis, or Ripley's K-function. So Ripley's K-function is actually, I think, one of the only tools where we're looking at clustering of the locations themselves. With all of the other tools, each of those points had to have a value. So in order to have clusters of high values and low values, each point has a value associated with it. But for Ripley's K, we're actually just looking at where the points are, and we're measuring to see if one feature being in the location attracts other features to be in that place too, or if it repels them. So we're again measuring clustering and dispersion, but this is kind of a spatial dependency. Does me being right here attract other people to be near me, or does it cause other people to want to be farther away from me? So
I have no comment on that.
So we also get a graph output for this one. And so we're comparing this to an expected distribution. So it's looking at it over different distances. Another thing that this does is measure if we have clustering or dispersion at different scales. So it's going to go through a bunch of different scales, and it's going to give us a line that we expect to follow with a confidence envelope. And then we look at the observed line. And so if we get a line like this, that means that the shorter distances, we have clustering, and at the farther distances, we see dispersion. Okay, so that's another tool set that we've wrapped up. Next is mapping clusters, which is one of our favorites.
Yes, it is.
So these tools, again, we're looking at clustering, but now we're going to be looking at local clustering. But first, we're going to look at the Similarity Search tool. This tool helps us to identify features that are similar to a feature of interest based on how similar they are by a set of attributes. So let's look at an example of that. Oh, wait, hold on.
Oh, yeah, sorry.
More of a hypothetical of that. So let's pretend that we have a point data set of potential store locations. I want to open a new store, and I can choose from any of these locations. I also have a high-performing store that I know a little something about. So I have some information about each of these store locations, the potential ones. I know the population density, the average income, and the distance to competition from each of these locations. And then I also have that same exact information for my high-performing store. So what I want to do is I want to rank my potential store locations by how similar they are to my high-performing store based on 3 variables: population density, average income, and distance to competition. So the tool is going to, depending how many results I ask for, in this case I'm going to ask for 5, give me the 5 locations that have the most similar attributes to my high-performing store, and the tool is going to rank those 5 locations for me with an output, and we can see how that looks like.
Okay, so that tool exists both in desktop and also ArcGIS Online. So I'm going to show it in ArcGIS Online because I just think it's really awesome that these tools are being exposed to so many more people now that they're in ArcGIS Online. And it's also just, I actually just started exploring data, and it's just amazing what you can do looking at something as simple as Similarity Search, especially when you combine it with geo-enrichment. So basically what I did is I have all these bike share locations, and first, and I have a location that I know we had an effect that's been doing really well, and I want to figure out what other places should we be expecting to do well based on the characteristics of that location. So the first thing that I want to do is I want to enrich those locations using geo-enrichment. And so perform analysis allows me to enrich my data, and once we enrich the data, we'll have all those attributes that we need to run Similarity Search. So we have thousands of variables that we can choose from. I chose data on, if we open up our table here, I chose data on age, population, per capita income, education. So I picked a couple of variables that I thought would be important or that were interesting variables to look at in terms of the success or the usage of these bike share locations. So the Find Similar tool allows me to find, first I choose that location that I'm interested in. That's my location of interest. And then I'm going to search from those enriched stores, from those enriched bike share locations, and I'm just going to choose the attributes that are important to me. And I can either choose to rank all locations from most to least similar. I can just say, show me just the one most similar. In this case, I'm going to choose to rank them all. I'll run my analysis, and the result of that analysis is that this store right here is the number 1 most similar store. It gives us the information about those variables. So we get all this information, but most importantly, we get these ranked store locations and we get a picture of their similarity. And there's a ton of applications for this. One of the big use cases that we had when we were building this tool was, I'm a local city or county, and from an economic development standpoint, I want to say, I'm just like these other cities, but here's how I'm better. So it can be really great for that kind of benchmarking. You say, I'm similar in terms of these characteristics, but here's all these ways that I'm different. So it can be really valuable from that standpoint. That was one of the big use cases we had. There's also a ton of commercial applications for the Similarity Search tool.
All right, grouping analysis. So grouping analysis allows us to find patterns in our data with multiple variables. So we actually group our features based on within the groups, them being as similar as possible, and between the groups, the features being as different as possible. So the output of a grouping analysis might look something like this. There are two different ways to run a grouping analysis. We can ask for a grouping analysis where we just want to group the features, but we don't need them to be spatially contiguous, so no spatial constraints. And to do that, the tool runs a k-means analysis. And so let's say that we have these points. And this is what they look like in data space, just by value, not in locational space. So we can ask for 2 groups, and it's going to split up this way. If we ask for 3 groups, it would split that way, or 4 groups. So it's really finding the natural places to split this data into different groups based on their different attributes. So finding areas in the data space that are more similar. If we choose a spatial constraint, it's a little bit more complicated because the features have to be near each other to be in the same group also. So the tool finds different seed locations based on how many groups you want as a result, and then it conducts a minimum spanning tree calculation, and then puts the features into different groups. So it looks at how different they are in data space, but also they have to be proximate in physical space. And to interpret the results of a grouping analysis, we look at a box plot, and so we can see each of those groups, how they compare to each other based on the variables that you input into the tool. So this is a cool one. Let's see how that works.
Yeah, it's definitely one that makes a lot more sense when you just see it in action. So for those of you out there who are big nerds like we are, this is one of the most fun tools just to play around with, because you learn a lot about your data and you can explore just the different relationships that exist in your data and how things group together. I could spend all day just running this on my data. I'm guessing there's at least one other person in this room that feels the same way.
That's me.
So this is data. We're looking at data. This is from the CCAPS Foundation. This is data about vulnerability in Africa. And so what they've done is they've basically created these, they call them baskets. And these baskets are different ways to kind of think about vulnerability. So one of them is about governance. So it's this idea that if something catastrophic were to happen, what is the likelihood that the government would be able to help the population in that area, or would be willing to help the population in that area. It's also a measure of transparency and what's the word I'm looking for? No, not vulnerability. These are all measures of vulnerability. It's about like corruption, that sort of thing. So that's the governance index. Another one is about household resiliency. So that's this idea if something catastrophic were to happen, what is the likelihood that the individual households themselves would be able to feed themselves? And this has a lot to do with income levels, education levels, employment, all those sorts of things. So there's those. There's also one about population density and another one about climate change and vulnerability to climate change. So all 4 of those variables. So this is essentially, you can imagine, each of those is a variable in this data set. And so I can turn on, let's say, the household resiliency index, and I can map that. Then I can go in and change which one I'm looking at. Let's say we look at governance. I can map that. So we can map all 4 of these variables, and you can imagine if this was demographic data, we could just create a bunch of different thematic maps and try to correlate them bring them together, do that grouping in our head, but that would get pretty old pretty fast. So the grouping analysis tool helps us make sense of all that data. So we're going to analyze the vulnerability data. We're going to create 4 groups, because I happen to know that that's the best number of groups, and I get that by evaluating the optimal number of groups here. There's a way to help you figure out what sometimes you just have a number that you need to create, right? Like I need to create 10 sales territories. That's an obvious, you put in 10. But if you're just trying to find the natural groupings in your data, this will allow you to find those by evaluating the data. So we're going to look at the population density, climate index, household resiliency, and the governance index. We're going to use no spatial constraint. And what's really cool about no spatial constraint is that even when you don't force it to be spatial, it usually is. And that's no surprise to any of us because everything's spatial, and it's the first law of geography, right? Things that are closer together are more related than things that are farther apart. It's Tobler's law. So it's no surprise that even when we don't force these things to be spatially contiguous, that we find these spatial patterns. And it's often the spatial patterns that emerge from this analysis that are the most interesting. So we get a lot of information from this analysis actually in our report. So if we go to the map, I think it's pretty obvious immediately, okay, we have these patterns, right? But knowing there's a green group isn't particularly useful. What's the green group? What's the orange group? We have no idea. So that's what this report is all about. It's only when we combine looking at the report with looking at the map that we start to really understand the results of this analysis. So we get a lot of information, and we are going to talk a lot more about this report in our session this afternoon. But I'm just going to focus on the parallel box plot. And so what this shows us, for instance, is let's say the green group. The green group, the higher this index, the more vulnerable. The large numbers are vulnerable. So what we see is that this green area is around average. So the black box plot represents the global average. And then each one of these colored lines represents where that group falls for that variable. So we can see that the green group is about average in terms of the vulnerability to climate. It's very vulnerable in terms of household resiliency, very vulnerable in terms of governance, and low vulnerability in terms of population density. Or we can see the red areas where there's high vulnerability in terms of climate index, but low in terms of household resiliency and governance, and about average in terms of population density. So we can see how each of these groups are vulnerable in different ways. So rather than just saying, okay, these are the most vulnerable areas, period, we can say these are vulnerable areas based on these characteristics. And these areas have these vulnerabilities. And so we can really use this information to understand those characteristics. And you can see, of course, that there are distinct kind of regimes here. So we see the orange area up here. It's pretty spatial, but it's similar to an area in other parts of Africa. So while we see that there's these spatial patterns, we also see that very distant places could have similar vulnerabilities also. So we get a lot of information just from exploring the spatial patterns that result from an analysis that didn't actually constrain the analysis spatially. So that's grouping analysis.
All right, next up is hotspot analysis. How many of you have run a hotspot analysis before?
Yeah.
It's usually the most popular tool. So I'm going to spend just a little bit more time on it, but I know that we are, still pretty tight on time. So a hotspot analysis is going to identify clusters of high and low values. So it's a local statistic, and it's not just going to tell us if we have clustering of high or low values. It's going to tell us where those clusters are. So I would like to talk a little bit about how this works, because I think that some of us might be using the tool without really understanding what it's doing. So let's take a look here at 45 of my favorite random numbers. And let's say
she's not kidding either.
It's pi, actually, if you
which
look
she
at
knows, like, how many digits of pi do you know?
That's irrelevant.
No, you have to tell us now.
Like 507. Okay, so let's say that I take 45 of my favorite random numbers, and I was to pick them up and shake them and drop them. Now, you don't really need to understand any probability theory to just kind of intuitively know, just really kind of feel that it'd be really unlikely that all of those high numbers would just happen to fall together right here, right? It's obvious that that's not random. But it's not always that obvious. So what a hotspot analysis does is it helps us measure the likelihood of that happening. What are the chances that this happened randomly? So let's take this to a map. And first, let's get clear on a couple of terms. So each of these polygons We'll call those features, okay? And around each feature, there's a set of features. Oh, I'm sorry. Each feature has to have a value. So again, we're measuring clusters in high values and low values. So each feature has to have a value. And we also need variance between those values, right? Because we can't have clusters of values if all of the values are the same. So each feature has a value, and we have variance between the values. The next term is neighborhood. So around each feature, and including the feature itself, we have a set of features, and we'll call that the neighborhood. And then all of the features, including the neighborhood, we will call that the study area. Okay, so what a hotspot analysis is asking is this neighborhood that was derived based on the original feature, is that statistically significantly different from the study area? So if that neighborhood is significantly higher than the study area, then that feature that the neighborhood was based off of will be marked as a hotspot. And we have 3 degrees of confidence for hotspots. You can be 90, 95, or 99% confident that that neighborhood is a cluster of high values, meaning that that feature belongs to a cluster. We can also be 90, 95, or 99% confident that a feature is a cold spot or belongs to a cluster of low values. Or if that neighborhood is not significantly different from the rest of the study area, so in other words, it's kind of random, then we'll mark that as not significant. So the tool goes feature to feature and asks, okay, what's your neighborhood? Is your neighborhood different from the study area? Yes? Okay, you're a hotspot. Next feature. What's your neighborhood? Is your neighborhood different from the study area? Yes? Okay, you're a hotspot too. And then we end up going through all the features and we have a hotspot map. So let's run a hotspot analysis.
Yeah. Okay. So I'm going to show you 2 examples of hotspot analysis. One of them is looking at obesity rates in Los Angeles County. This was my the data from my thesis, so I hate it with a passion. But I'm going to show it to you anyway. So we're going to use optimized hotspot analysis, which is a tool that uses under the hood hotspot analysis and is optimized to make it just really easy to run. And we're going to talk in a ton of depth about, we're going to go into even more depth than Flora just did about hotspot analysis and the decisions that you need to make and what optimized hotspot analysis is really doing under the hood in the session this afternoon. Today, you're just going to, right now, you're just going to have to take my word for it that it's awesome and is doing a really good hotspot analysis. So we're going to run the analysis, and it is going to create those, that map for us. And we can, oh, I ran it on the wrong variable. Like that, I know what the hotspot map of this data looks like.
Results window.
Yes. Yay, results window. Okay, %5b. That is the actual variable that has to do with childhood obesity. So this is the percentage of 5th graders in each of these school zones that were overweight or obese. In some of those places, it's over 50%. And so these are the areas, and we can see based on the colors, the places that are where we have more confidence, the places where we have less confidence. And we actually built optimized hotspot analysis with ArcGIS Online in mind because we really wanted to get hotspot analysis into the hands of a lot of people and into the hands of people. So how many people have run hotspot, the Getis-Ord GI-star statistic hotspot tool and accepted all the defaults? Oh, please. Fine. You don't have to raise your hand, but you know. I know, it's true. So that's why we built optimized hotspot analysis. The thing about the one we build tools is once we build a tool, it has to, essentially, we have to make sure that a model you create with one of our tools works forever, essentially. That's our goal. And we can't just go willy-nilly changing what the output will be. So the defaults are what they are, and what we've done is for optimized hotspot analysis, we've basically created a new set of defaults so that the defaults are really based on us interrogating your data, evaluating the data, and making decisions based on that data. And so this is an example of using that. This is graffiti incidents in New York City, and if we go to perform analysis and we go to analyze patterns, we can find hotspots. If we have no analysis field, we have options to either provide our own polygons. So here we could use police precincts, for instance, or beats. We could also use a bounding polygon that would say where these incidents could have happened. Oh, I did the other way around, but you could provide either of those. Of course, you could provide an analysis field. But in this case, I just let it create the grid for me, and we can see the result of that analysis. And if I click on one of these locations, I can see like the lighter pink one is a hotspot where we have 90% confidence. So now you can do this kind of analysis right inside of ArcGIS Online and really get this analysis also into the hands of more people that won't know the ins and outs of hotspot analysis but can still do a valid analysis.
All right, last in this tool set is cluster and outlier analysis. So cluster and outlier is similar to hotspot analysis in that it finds clusters of high values and clusters of low values, but it also identifies outliers. So let's take a look at how that works. So again, we're separating the feature in the neighborhood from the study area. But now instead of just looking at whether the neighborhood is different from the study area, we're asking, is the feature different from all other features? And is the neighborhood different from all other neighborhoods? And so we have 4 different answers. So if the feature is significantly higher than all other features and the neighborhood is significantly higher than all other neighborhoods, then we have a high cluster. If the opposite is true, the feature is lower and the neighborhood is lower, we have a low cluster. But we can also have a situation where the feature is significantly higher than all other features, but the neighborhood is significantly lower than all other features. In that case, the feature is going to be a high-low outlier. And the inverse, if the feature is lower than all other features and the neighborhood is higher than all other features, then we're going to have a low-high outlier. So a cluster outlier map might look something like this. Where the lighter pink are the high highs, and the lighter blue the low lows, the bright reds the high lows, and the dark blues the low highs. So if I graph the results of this cluster outlier analysis, so here I'm looking at the values versus the z-scores. And we can see here that if the z-scores are low, then we have outliers, and when the z-scores are significantly high, we have clusters. And I can draw this on the map here. So again, the high highs, the low lows, high lows, and low highs. So every of these values is falling somewhere in the quadrant, but you have to be significantly high or significantly low enough. So you'll notice that in the middle here, we have the gray features that were not different enough to be marked as statistically significant. So let's see that in action.
All right, so we're going to use that same dreaded Los Angeles data to do a cluster outlier analysis. So one of the things that we sometimes use optimized hotspot analysis for, one of the things that we create in the messages window, we do a bunch of evaluation, and we'll talk about that this afternoon, but we evaluate what's the optimal distance to use for our hotspot analysis. What's the optimal distance to use for our neighborhood? And this is when This is when you don't have one in mind, one that makes sense for the question that you're asking, and you're just trying to get the tool to help you start to explore what might be an ideal one. But we'll talk about that more later. But we're going to use that distance when we run cluster outlier analysis. So I'm going to run the analysis using that same data. I'm going to use the right variable this time. We're going to use a distance band. This is where we define what it means to be neighbors, how we define that neighborhood. We run that analysis, and it's going to return to us this report, so this map. So what we see here, we see a similar pattern to what the hotspot analysis showed us, but what we can see is that within that hotspot, there are actually these clusters where we have low values that are surrounded by high values, and those can be incredibly important, especially if you think about something like obesity. How did these areas manage to have such low rates of obesity surrounded by places that are, in theory, quite similar to them? They are close by. what are the things that they're doing right that we could try to mimic in other places, for instance? Or we can see the high-low clusters. What are the things that they're doing wrong? How are they failing when others around them are doing so well? And so those outliers can really drive a lot of new questions and can help us, especially when we move into exploring relationships, they can help us get into other if we know, okay, well, this one's doing well and these aren't, maybe I'm missing a variable, maybe I haven't taken something into consideration, and those can help us find some of those variables that might be really critical.
All right, so that was the end of the mapping clusters tool set. And this afternoon, we were really going to spend the whole 75 minutes talking about just that tool set and those 4 different tools. So let's wrap this up now with modeling spatial relationships. Okay, so this tool set has some regression analysis tools and a couple other tools to help us define the relationship between different features. So we'll start first by talking about the Generate Spatial Weights Matrix tool. And this tool creates an SWM or a SWIM file. And basically, it helps us answer that question of how are neighborhood sizes determined. So if you remember when I talked about hotspot analysis and cluster and outlier analysis, I said that we were looking at that neighborhood. And you might have been wondering, well, how do I know what the neighborhood is? Well, there are different ways to do this. That incremental spatial autocorrelation tool that we talked about earlier is actually how the optimized hotspot analysis tool picks that neighborhood. It looks for that peak distance, and that becomes the neighborhood. But you have more flexibility with the Generate Spatial Weights Matrix tool. You can define the neighborhood however you'd like. So there are lots of different ways to do it. I'm just going to talk about one of the ways, which is one of my favorites, which is k-nearest neighbors. So with k-nearest neighbors, you're looking at K stands for kind of like the number. So let's say I'm looking at 4 nearest neighbors in this example. Each feature is going to have a neighborhood composed of its 4 nearest neighbors. So it doesn't matter how far those 4 nearest neighbors are, it's whichever ones are the nearest. So each feature's neighborhood is defined that way. The next tool is similar. It's Generate Network Spatial Weights. And this tool is also going to create a SWIM file. But in this case, we're looking at distances based on a network. So let's say we want to look at a drive time instead of a Euclidean distance, because we want to see how the relationships between these features vary when people are traveling from one place to another. So each feature will have the drive time, and that will become the neighborhood. And that's how we'll decide what the neighborhood is for those other analyses, like hotspot analysis and cluster and outlier analysis. Next is ordinary least squares, and this is a regression tool. It's a linear regression tool, and what it helps us do is estimate the relationship between different variables. So I'm going to go through these last 3 tools, the slides, really quickly, and then Lauren's going to talk about them all at once so that we're not jumping back and forth since they're very closely related. We also have an exploratory regression tool. So this tool it helps us find a properly specified ordinary least squares model. So it actually tries lots of different combinations of all the different variables to help you find a properly specified model. It's kind of like an iterative process, and it tries different combinations of 1 variable to 5 variables and gives you a lot of really useful outputs for looking at how often a variable might be significant in your analysis. It helps you look at correlations, and it might also help you find a properly specified model. So we have a whole other workshop on regression analysis and properly specified models. So I'm not going to really teach you how that works right now, but please come back if you would like to learn more.
It'll be the most fun you'll ever spend learning about regression analysis.
I think it's really true.
I promise.
And then lastly, geographically weighted regression. So again, it's a linear regression model, but this time we are looking at neighborhoods. So each feature is going to get a separate equation. So we're actually going to be able to see how a model performs over space. So based on that feature's neighborhood, it gets that one equation, but then each feature will get its own equation based on its neighborhood. And so then we can see how that local R squared varies over space. We can see where the correlations are strongest, and that might help us with focusing our efforts when we try to address the issue at hand. So let's take a look at some regression results.
All right, this is our last demo, and since we have 3 minutes, I think we planned perfectly because
can't believe it.
I know, it's amazing. It's a miracle. We also don't have a session immediately after, so we can totally take questions, and we're going to be around, and we have a lot more sessions. So next year we'll leave 10 minutes, but I think it's a real miracle we got this far. So Medicare spending, this is actually kind of a sneak peek at the topic that we'll be looking at in our regression sessions. We're looking at Medicare spending. And this is just a quick little kind of story mappy type of thing that helps us walk through that analysis. So what I really want to show is this. So this is the Medicare spending data. Now, in a perfect world, we would think that we'd be spending about the same amount per capita on every person on Medicare, right? Now, we'd expect to be spending a little more on one person, a little less on others, but we wouldn't expect to see whole regions of the country where we're spending a lot more per capita. And this is taking into account things like cost of living differences, age of the population. This is adjusted for that. We would expect there to be a randomness. But of course, I'm sure it comes as no surprise to anybody in this room that it's not random at all, and that there are clusters where we're spending a lot more per capita. And so our question is why? And regression analysis helps us answer those why questions that a lot of the mapping clusters tools bring up. We see the pattern. It's not like my research in childhood obesity was, okay, well, now we know where all the obese children are. My job is done, like we want to know where those patterns are so we can do something about it. So our first question naively was maybe we're just spending more money where people are sicker. So we did a hotspot analysis of where people are sicker, and obviously those things are not related. We also thought maybe people are just getting better care in those places where we're spending more per capita. That's obviously not true either. So we looked at that. That also didn't really correlate. Actually, we saw that people were getting better care in the places where we were spending less per capita, which might come as no surprise to some of you. So we used exploratory regression to explore what are some of the factors related to spending in each of these areas. And exploratory regression lets us explore those correlations. So one example is we found in this part of the southern United States, we saw that imaging events was a really good predictor of spending. So that means the more times people are getting CAT scans and MRIs, the more spending there is. And there's a lot of research on this idea that it's amazing how once a doctor has an MRI, once they've just gotten a new MRI machine, everyone seems to need an MRI. No offense to doctors in the room. I'm sure none of you do that. But these kinds of things, and these are things that we can actually do something about, right? If it was just people are sicker here, there's not a whole lot we can do about, well, we can try, but we might end up spending more money. But it's the things like the way that medicine is being practiced that we can really do something about. Or dehydration admissions is another example. Educating people about educating people about the importance of hydrating elderly patients, because that's a big reason that a lot of elderly patients end up in the hospital. So we spend money and it's totally avoidable. So we did this analysis, and finally we found in this area a properly specified model, and we used geographically weighted regression to see where each of these variables was most significant. So we can see, for instance, that the darkest area here is where imaging events are a good predictor of Medicare spending. Now, we're going to get all into how geographically weighted regression works, but the idea here is that we can focus our resources based on where those variables are important. So if we know dehydration admissions is a good predictor in this area, we can focus those educational policies here. If we know MRIs are a good predictor here, we can focus those policies there. Now, in a perfect world, we could just put all policies everywhere because we have unlimited resources, but resources are never unlimited, and so being able to focus those resources in the places where we're going to get the most bang for our buck is what GWR is all about, and we're going to talk a lot more about that in the next session. So that...
All right, so thank you so much. Please fill out a session survey. We'd really like your feedback. We always want to improve.
It's our first one,
we
so
really
please
appreciate
give us
you
the
letting
feedback.
us know how we did. And also more courses if you'd like to learn more.